All right, so chapter 13 is about this concept called rates. Rates. Okay, so what do you think about when I use the term rates? There's no wrong answer, so what do you think of when you hear the term rates?
Speed.
Yes, exactly. How fast or speed? Okay. How fast the reaction is going, or the speed of a reaction. So what is your speed when you came to work today or you came to school today? Maybe it's miles per hour. Okay, maybe if you came to school in a car, if you came to school in some sort of jet, or if you're walking, maybe if you're walking, it's steps per minute. Okay. Anyways, when we talk about speed, there's one thing that we have to introduce, and that is time. Okay, time. So anytime you're talking about how fast or speed, we have to include some dimension of time. So the SI unit, SI base units. So the SI base unit of time is seconds. Okay. And speed usually conveys some distance. Okay, feet, inches. Okay, but we're in chemistry class. So instead of distance over time, it's going to be concentration over time. And in chemistry, just by default, it's not always this way, but at least in this chapter, it's going to be, the concentration is going to be molarity, moles over liter, moles of solute over liters of solution. So this is how we measure our speed. Okay, so this bracket here, this bracket here represents concentration in moles over liter, moles of solute over liters of solution.
So the one equation of the will represent concentration, correct?
So this bracket here is moles of solute over liters of solution. We know this as molarity. Okay, which from our exam is moles of solute over liters of solution. Okay, so if I use the brackets term, what do I mean? I mean molar. Okay, what is molar? Moles of solute over liters of solution. So this is our speed. Okay, in chemistry terms. In chemistry terms, this is our speed. As you mentioned, Eric, this is how we measure how fast. All right, so two things when we talk about rates, how fast, we have to include some sort of time element, and in chemistry that's usually seconds, but it may not be seconds. You may get a problem where it's in minutes. It's okay. And some concentration, which it's going to be molarity, but you may have a problem in your homework where it's millimolar, micromolar, or something. Okay, but this is how we assess how fast a reaction proceeds.
So the equation of the boiler is basically molarity over seconds, essentially.
Some concentration over time. Some concentration over time. Time does not always have to be in seconds, but the SI base unit of time is seconds. So consider this reaction. A goes to B. Okay, I have a reaction A goes to B. Okay, A is the reactant, B is the product. Okay, so we're going to plot over time what happens. We'll put time on the x-axis, and we're going to put concentration on the y-axis. Okay, don't forget these brackets mean concentration. So what do you think over time is going to happen to the concentration of A? Over time. Okay, it will go down. Is this correct? Yes, because it's being converted to product B. What's going to happen to B over time? Over time, what will happen to the concentration of B? Yes, it is going to increase over time. All right, so we are tasked, okay, we have to figure out how fast this is happening. A goes to B. Is it happening fast, slow? We can't just use words fast or slow, okay? We have to put some time to it, okay, some number attached to how fast this is. I just also want to tell you that the concentration of A, so this is going to be the change in concentration of A. Just got to make sure I get this right. Over some increment of time. Okay? Change in concentration of A over some increment of time. This is going to be minus. Okay? This is going to equal to the change in concentration of B. Okay, that's fine. Over change in time, some increment of time. Okay, some window of time. A is going to go down, and what's going to happen to B? Go up. Okay, because it's 1-to-1. This is a 1-to-1, 1 mole A to 1 mole B. This is the relationship. Okay, notice here. What did I put? Okay, why is it negative, Bailey?
Because they're inverses of each other. What they're doing is basically inverse. So that's like A goes down, B goes up.
Correct. That's why A is negative. A is negative. Why is A negative? Because it's
going down.
It's going down. Why is B positive?
Going up.
Because it's going up. Okay? So this is called the rate expression. Okay, we'll do a rate expression problem. All right, so that's point number 1. Okay, rate expression. Okay, point number 2, which we'll talk about, is called a rate law. This is something you'll see on your quiz and on the exam. Okay. So fast, how fast? So we can use a rate expression. How much in proportion is this going down, reactant, as this product going up? But there's also a rate law. Okay, there's a rate law. So let me give you the formula for the rate law. Okay, now this is tricky. Okay, the rate, which is how fast, okay, is going to equal to some constant k, lowercase k, times the concentration of A, the initial starting material, and that concentration of A is raised to the power of, I'll just call it x. Okay. This is called the rate law. All right. All right. So first we'll do number 1. Okay. Then we'll talk about number 2. So this is an equation. Just this number 1 just tells you how much is going down versus how much is going up. But this is an equation. This is an actual equation that describes how fast. This is an actual equation that describes how fast. Notice here how fast depends on the starting concentration of your reactant. Okay, this is for the equation A goes to B. For the equation A goes to B, the rate law is, okay, the rate equals K times the starting concentration of A, your reactant. How much you start with determines how fast the reaction is going to go. All right, this K here is called the rate constant. All right, so if this is a little confusing, we'll talk about it more as we go to page 2, 3, 4, and 5, so on. Okay. But this lowercase k is the rate constant. Every reaction will have its own rate constant, lowercase k. Is this something that I will give you on the exam? No. Why? Because there's millions of reactions. I can't give you millions of rate constants. Okay, there's millions of temperatures. every rate constant will be different at a given temperature. So we have to find this. Okay, we have to find this. Okay, in our homework problems, quiz problems, test problems, we have to find it. So let me tell you some attributes. Okay, let me tell you some attributes, features of rate constant K. Okay, this is the one constant in this class where I won't give it to you because it's not universal. Okay, it changes depending on your reactions. First of all, not all reactions are just plain old A goes to B. Okay, obviously there's reactions that are like this. A plus B goes to C plus D. So obviously the rate constant for this reaction, K, will be different than the rate constant for this reaction, K. Okay? So we have to find lowercase constant K, lowercase k. Okay? All right, so first of all, number one is that we have to find it. We have to calculate this. We're talking about rate law, okay, not rate expression. Number two, it's quoted at a specific temperature, just like vapor pressure way back in chapter 12. You change the temperature, you change the rate constant. Okay. Number three is that this is another tricky aspect to it. The units will vary. Okay, the units vary. Okay, so not only do we have to calculate it, we have to calculate it with the right units. Because this reaction will have a different rate constant with different units than this reaction, which will have a different rate constant with different units. Okay, let me write the rate law for this reaction here. Okay, this is going to be rate is equal to K times the concentration of A. This is going to be raised to some power. I'm going to call it X. Remember, how fast something occurs is based upon the starting material. And there's another starting material, reactant B, and that's raised to the Y power. So this is the rate law for this reaction. This is the rate, A plus B goes to C plus D. Here's another important point I'd like to convey to you guys as a class. How fast is this happening? Because as our classmate Eric mentioned at the very beginning, rate means how fast. Rate means how fast. So how will we determine how fast A goes to B? How will we determine how fast A plus B goes to C plus D? How will we determine this? Okay, we will determine this by the decay of A. We will determine this by the decay of A and the decay of B. So we determine how fast based on the decay of A. This is our measurement to determine how fast the reaction is going to occur.
So it's the decay of A, essentially, what you're saying?
Yes, not the appearance of B, but the decay of A. You're right, Bailey. So this brings me back. So it's the same thing with this one. Okay, if I were to draw a graph of A plus B goes to C plus D, okay, what's going to happen to the concentration of A over time for this reaction? What's going to happen? Correct. What's going to happen to B? Okay, we don't know if it's going to be higher or lower, but it's going to decrease. Okay. What's going to happen to C? Very good. What's going to happen to D? Okay, we don't know whether it's going to be, to the left or right, but it's going to increase. Okay, we don't know if it's going to be, this way or that way, but we know it's going to increase. So this is where this exponent comes in, okay? This exponent. Okay, this exponent is x raised to the power of x. Okay, I just said x. Okay, here a is raised to the power of x, b is raised to the power of y. This exponent x, y, and z is called the order of decay. Order of decay. It is the exponent. Okay, because we don't know how this will decay. We're measuring how fast based on decay. How many of you have heard the term first order decay, second order decay? Maybe? No? Zero order decay? Well, how many of you have heard the term half-life? Can raise your hand. Okay, everyone, most of you have heard the term half-life. Okay, this is where half-life comes from. Okay, this is where half-life comes from. So this x, exponent y, is called the order of decay. And for this class, it will either be three values. We'll have zero order decay, first order decay, or second order decay. These are the exponents x and y.
So x and y are the order of decay?
Yes. So if this x exponent is 0, that means A is decaying with 0 order kinetics. If this x is 0, that means the exponent is 0. This reactant A is decaying with 0 order kinetics. Okay, so it can be 0. That means the reactant is decaying with 0 order kinetics, and it has all those different equations for 0 order kinetics, which they're on, you don't memorize that. I'll give that to you. Okay, if this exponent is 1, let's say this is 1, A is decaying with first order kinetics. If this y is 1, B is decaying with first order kinetics with all the different first order equations and first order half-life. And then finally, there's only going to be 3 answers for this. Okay? If your exponent x is 2, that means A is decaying with second order kinetics and all those equations, second order half-life. If your y is 2, that means B, this reactant B, is decaying with second order kinetics and all its associated equations, which are actually on page something in your book. Okay, page 9, I think. Page 7.
So under like the A to B one, when you say we have to calculate this, are you talking about the exponent?
Yes, and K. Very much so. You're right. Okay, so when we do these rate law problems, which students in all my 9-10 years here, I think it's going to be 10 years in August. Okay, they always, someone or the other, some student or the other will always mess up this problem because you have to calculate, as Bailey said, the K with the right units. And you have to calculate how is A decaying. How is this reactant going to decay? It will either decay with 0, first, or second. Okay? So this is what we will be encountering for the next 1 or 2 weeks. Okay, how to do a rate expression and how to do a rate law. All right? So in terms of tests, in terms of exams, I am keen on rate law. Okay, so if you look at your quiz, your homework, okay, this is what will be on the exam. Okay, so we will focus our attention on this.
Oh, so is the rate law for the A plus B produces C plus D? Where is that rate? Where is that rate law?
This is the rate law. We have to calculate K, and we have to calculate how A decays, 0 first or second, and we have to calculate Y, the exponent Y, which is how B decays. Does it decay 0 first or second? And this is good questions. And then K is what you have to calculate.
So the rate is basically the same as the rate law, essentially.
This is the form of the rate law.
Oh, okay.
This is the form of the rate law. Okay. Those are good questions. But it will become clear. Hopefully there's some clarity when we go to the pages here, okay, in our notes. All right, so this rate constant K, we have to calculate this. It's not a constant I give you. it's quoted at a specific temperature. So if you change, actually, if you increase the temperature, if you increase the temperature, the reactions go faster, and that means the rate goes faster, which means K goes faster. Okay, the units are going to change, okay, because it depends upon whether this reactant decays with 0, first, or second order. And then the final thing I want to say, just as a disclaimer, okay, is just as a final disclaimer, do not confuse with capital K. Okay, capital K. Okay, so this capital K is called the equilibrium constant, which is something that we will talk about in chapter 14. We don't talk about it. We don't concern ourselves with it. We concern ourselves with lowercase k, which is the, like I said, rate constant. This is something totally unrelated. Okay, so don't confuse your k's. Special k? No. Don't confuse your k's. Okay, lowercase k is the rate constant. So I'm going to move on to page 2. Let's talk about rate expression very briefly, and then we'll focus most of our attention on rate law, see how far we can get today. All right, I will scan these notes once class is over. This is something that you guys could look at in your notes, independent from me, but kind of what I've been mentioning to you guys before. Anytime you have rates, okay, there's going to be a time component over time, and over time, reactants will decrease, products will increase. Okay, and this is the rate of change over time. Okay, rate of change of time. This is actually a little bit of calculus. How many of you have had calculus? Okay, you've had calculus. Oh, very good, nice, good job. I had calculus, but I forgot it all. So yeah, if you don't use it, you lose it, right? So so it's a little bit of calculus here, but there's no calculus in this class. Okay, so why is this minus? Why is this minus? It's a reactant that's going to go down. And yes, very good. And why is this positive, Maria? It's a product that's going to increase, okay, over time. Over what? Time. Okay, just want to illustrate over time. Okay, anytime you have rate, there's going to be time components added to it. All right, let's do a rate So this is not something I'm going to emphasize, but I want to introduce it to you because you may get some exposure to it for your future studies. Okay, rate expression. Okay. Look at this reaction with me. Okay. So 2H2O2 goes to 2H2O plus oxygen gas. All right, so what's going to happen over time with the concentration of H2O2? It will decrease. So the change in concentration over time change in concentration over time of hydrogen peroxide, increment of concentration of this over an increment of time, okay, will decrease. So there's the minus sign. Okay, why is there a minus 1/2 here? Okay, because of the stoichiometry. Okay. So this, because it's a 2-to-2 ratio, okay, this disappearance will equal to this appearance of H2O. Okay. is it positive or negative? It's positive. Why? It's a product. Okay? And how many moles for this mole? For this mole, it's 1 to 1, so it's going to be 1/2. Okay? And that's going to equal, so this disappearance will equal to the rate of appearance of this, as well as this disappearance will equal to the rate of appearance of this. Okay, but notice this is a 2 to 1 ratio, 2 to 1. So first of all, will this be positive or negative? It's a product. Positive. So the rate of change in concentration of O2 over some window of time will be positive. Okay?
So wait, why is it 1/2 again? I don't know.
Because of the stoichiometry. For every 2 moles of this, there's 1 mole of that.
Oh.
But when they react, for every 1/2 mole, this will react. For every 2 moles of this, there's 1 mole of that. But when this decreases, it's going to be minus 1/2, minus because it's a
Okay, but then
reactant.
why is the H2O, why is that the 1/2 then?
Because this is in a 2 to 2.
So then why is it like 1 to 1 then?
You can make it 1 to 1, yeah.
So it could be just, so you could just leave just like 1 to 1 then?
Yes, you can make it 1 to 1, just like that.
Okay. I'll throw it for you. I think I have to.
Yeah. Yes, okay. The 1/2s cancel. So because it's 2 to 2, or as she's mentioned, 1 to 1, the rate of disappearance of this will equal to the rate of appearance of that. But what about this in respect to that? The rate of disappearance of this by 1/2 will equal to the rate of appearance of this, because it's 2 to 1. 2 to 1.
So then why isn't the O2, why is that not 1/2 then?
Because there's only 1 mole here.
Okay. Oh, so we're looking at like the oxygen, like this, and like that's what that's like one of the products there. That's what like we're kind of looking at.
Yes.
Okay. Oh, I see. So in case like in oxygen.
Yeah, you take the reciprocal. Okay, for the rate expression. If I'm talking mumbo jumbo, just take the reciprocal. Okay? Take the reciprocal of the coefficient. But which one becomes the minus, the reactants or the products? Because they're going down over time, which becomes positive because they are increasing over time. Okay, this is the rate expression. Is this the rate law? No. No. Okay?
You take the reciprocal of what again?
The coefficient. The stoichiometric coefficient. Okay?
Oh, okay. So that's what you do is take the reciprocal coefficient.
Yeah, just for rate expression. Okay? If you have gases, this gets a little bit more complicated. Let's say you have a gas. The gas can be expressed in terms of concentration. Okay? Or the gas can be expressed in terms of pressure. Okay, gases can be expressed in terms of concentration. Or pressure P. So anytime you see a gas, we may see a pressure or concentration. Concentration is in moles per liter. Okay? So this would be, you take that previous, so I'm not going to focus on this on the exam, but you can also do this as a pressure. Okay, so it's going to be either as concentration or because this is a gas, pressure. pressure of O2 over time. Okay. Right. Because it's a gas, you can express it either as a concentration, which I'm doing here, or you can express it as a pressure, which I am doing here.
So in terms of the expressions, so the products are always positive, correct?
Yes, because they are increasing over time. All right. And if you see a gas, like here, if you see a gas, you can express that gas in change in concentration of the gas over time or change in pressure over time. Okay? That's all this is saying here. That's all this is saying. Change in pressure of O2 over time. Okay? So this T here stands for temperature. This lowercase t stands for time. Change in time. Okay?
So is it the RT or the RT delta T?
Capital T is temperature, delta T is time.
Okay.
Lowercase t is time. And this is stemming from the ideal gas law, which is what we talked about way back in Chem 1. All right, so gases, you can put change in the concentration or the change in pressure. All right, let's do let's see here, what do I have here? Okay, let's do a problem here, and then we'll go to rate law. All right, RUT is the rate expression for the following reaction. Okay, so the rate expression, the change in concentration of CH4 over some change in time, some increment of time. Will this be positive or negative? Okay, that's going to equal to, what's the proportion of this? 1 to 2. So this is going to be positive or negative 1/2. Okay, negative 1/2, the change in concentration of O2 over that same window of time. Okay, because this is a 1 to 2 relationship, you take the reciprocal. Okay, this is going to equal to the change in concentration of CO2. Will that be positive or negative, and what would the fraction be? Okay, there's just 1 mole, so for every 1 mole of this, there's 1 mole of that. So as this decreases, this will increase 1 to 1. And this is going to equal the appearance of this, the appearance of CO2, and the appearance of this. Okay, but what will the appearance of this be? Will it be positive or negative? It will be positive, but this reacts in a 1 to 2. For every 1 mole of this, you produce 2 moles of that. So what will this be? 1/2. So that is the rate expression. The rate of disappearance of this equals to minus 1/2 the rate of disappearance of this, because it's also a reactant, which equals to the rate of appearance of this, which equals to 1/2 the rate of appearance of this, because again it's 1/2, 2 moles. All right, so this is how you write a rate expression. So now let's shift gears here and talk about the rate law. So this is something that I consider kind of important, and so we will do a rate law problem now. All right. So is everyone okay? We did an example of a rate expression. I believe your homework, there's a practice problem that you can do as well. Okay. right, so if everyone is okay, we'll now focus on the rate law. Okay, not rate expression, the rate law. And actually what we can do is, so we have an example problem that's worked out here, so I'll let you guys look at that. And that is also continued on page 5, the worked out problem for the rate law. So I'll let you look at that. Okay. And then we have our final answer for this rate law problem here on page 6. I'll let you guys look at that. This is the final answer that we get. Okay, don't forget the units. So we have a worked out problem here. Let's do the problem together now. All right. All right, so we have up above is a worked out problem. This is a problem that we will work on together. All right, so the reaction of S2O8 minus 2 with I minus is this, okay, shown here. Okay, so here is our reaction. Okay, and the question is, what is the rate law for this reaction? So also given to us, this is be given is a data table. Okay. So let's look at this table together. Okay, what are the reactants here? S2O8 minus 2, and what is the other reactant? 3I minus, very good. So here in experiment 1, this is the concentration of S2O8 minus 2. This is the concentration of I minus, and this is how fast the reaction went. 2.2 times 10 to the minus 4 molarity per seconds. Okay, rate, molar per seconds. Okay, so that's how fast these two reactants are generating these two products. Right, let's look at experiment 2. Okay, they kept this reactant constant. What did they do to this one? They changed it. Okay, so they actually, they changed it. And this is the resultant speed of this reaction. Let's look at experiment 3. What did they do in experiment 3? These two stayed the same, but what did they change? Okay, the S2O8 minus 2. Okay, and when they did that, this was the reaction they got, the speed. Okay. All right, so we're going to find the rate law for this reaction. What is the rate law form? Okay, so you start out by writing the rate law form, which is rate is equal to, very good, lowercase k times. So this reactant is going to decay with some order of kinetics. We'll call it A, lowercase a. We need to find this. Will S2O8 decay with minus 2 decay with 0 order, first order, or second order kinetics? Okay, what about the I minus? Okay. This reactant is also going to decay either with 0 order, first order, or second order kinetics. This B is not 3. First of all, there's no such thing as third order kinetics. Okay, if there is, it's beyond the class. Okay, so it's not 3 just because there's a 3 there. This is just to balance the moles. But how I minus decays, we have to calculate it. How S2O8 minus 2, how it decays, okay, we have to calculate it. How this decays and how that decays determines how fast the reaction is going to occur. All right, so we need to calculate K, A, and B. All right. So we're going to compare. The first thing we'll do is we'll compare. I'm going to compare experiment 1 and 2. You can compare any ones you like, but I'm going to compare 1 and 2 together. Okay, you'll see why. We're going to compare experiment 1 with experiment 2. Okay, so that means rate 1 over rate 2 is going to equal to, we'll do this here. K times S2O8 minus 2 raised to the A times I minus raised to the B. Okay, we'll do this in black here. Okay, so in the numerator we're going to have experiment 1 values, and in the denominator we'll have experiment 2 values. Okay, just going by this equation. Okay. All right, let's substitute. What is rate 1? Do you all agree it's 2.2 times 10 to the minus 4 molar over seconds? Okay, what is rate 2? Do you all agree it's 1.1 times 10 to the minus 4? All right, equals K. We don't know K. What's the concentration of S2O8 minus 2 for experiment 1, rate 1? What will it be? What will it be? Go ahead. Raised to the power of A. Okay, Antoinette, what is I minus for experiment 1, rate 1? Okay, raised to the power of B, its order of decay. Divided by this K, which we have to calculate later. What is S2O8 minus 2 for experiment 2, rate 2? Same thing. And what is I minus, Antoinette, for experiment 2, rate 2? Okay, raised to the B power. Very good. All right, is everyone okay with this so far?
So how'd you get, why does it take the M, why is the M to like the power of their?
Because the units are molar.
Oh, you can use the
So the mole over seconds cancels. And also the 0.08 to the power of A cancels out to the 0.08 to the power of A, and the K's cancel. Okay. So this becomes 0.034 divided by 0.017. Okay, the m's cancel also, just so you know. Okay, that whole thing raised to the power of b. Okay, I just kind of grouped the whole thing to the exponent b. And this is going to equal to, what's 2.2 times 10 to the minus 4 divided by 1.1 times 10 to the minus 4. Okay. Okay, I know this to be 2. Okay, so this is going to equal to 2. All right, so what's 0.034 divided by 0.017? Okay, if you do that on your calculator, this is going to be 2 to the power of b. Huh?
No, it's 2.
Yes, to the power of b. Okay, you want to see how I got from here to here? Okay, I canceled this, I canceled this, I canceled the k's.
So wait, then what happened to the b again exactly?
It's here, it's the exponent.
Okay, but then, so then do we have to solve for b then?
Yes. I just moved the brackets out. Okay. Okay, so what's the answer for b? What will b be? Is it 0? What's 2 to the power of 0? It's 1. What will b equal to 1? Okay. Will b equal to 2? 2 to the power of 2 is 4. So b is equal to 1. And what does that mean? Okay, it means that I minus decays with second order kinetics. No, I minus decays with first order kinetics. Sorry.
How do we determine that it's 1? Like, what does it have to equal exactly?
2 to the power of b is equal to 2. What is b?
So it has to, so what we have to do is make it true, okay.
Yes, 1 makes it true. Okay, so I minus decays with first order kinetics. Okay, so this I minus is going to decay with first order kinetics.
So k equals 2, and then the
K is rate constant,
Oh,
and
no.
that's not. B equals 1. Okay, B. Okay, which is what I put for I minus. It's order of decay. Okay, so I minus is going to decay with first order kinetics. All right, now we're going to calculate exponent A. We need to determine this reactant, whether it will react with 0, first or second order. All right, so for that, I am going to compare experiments 2 and 3. Okay, let's compare experiments 2 and 3 now. I'm going to compare experiment 2 with experiment 3. All right. So rate 2 over rate 3, okay, is going to equal to K times S2O8 minus 2 raised to the A power times I minus raised to the B power. We already know B is 1. Divided by K S2O8 minus 2 raised to the A power times I minus raised to the power of B. Okay? And we know B is equal to 1. So what is rate 2? Okay, what is rate 2? In our notes, rate 2 is 1.1 times 10 to the minus 4 molar over seconds. What is rate 3? 2.2 times 10 to the minus 4. Okay, I'm just plugging stuff in. All right, K we don't know. What is experiment 2, rate 2, S2O8 minus 2 concentration? Okay, rate to experiment 2 is going to be 0.080 m raised to the power of A. Okay, what is I minus for rate to experiment 2? Okay, 0.0107 m raised to the power of B, which we know is 1. B is equal to 1, by the way. Okay. Okay, now we'll plug in rate 3, experiment 3 values. So what is S208 minus 2 for experiment 3? 0.16 big M. And what is I minus rate 3, experiment 3? 0.017 big M raised to the power of B. Okay, remember B is equal to 1. But that's okay, B equals to 1 or not, because this will cancel with this. The k's cancel. We have to calculate them later. Okay, this unit cancels. So I'm going to take this individual exponent A and group it out. Okay, m's cancel. Okay, I'm just making the common exponent A across the whole fraction. What's 1.1 times 10 to the minus 4 divided by 2.2 times 10 to the minus 4? Okay, I can do that in my head. That's 1/2. And what's 0.08 divided by 0.16? That's also 1/2. That's also 1/2 to the power of A. So what will A be this time around? Okay. Will A equal 0? No. Will A equal 1? Or will A equal 2? Okay, 0 order, first order, or second order decay. Okay, A is going to equal to 1. Okay, so A is equal to 1. So just like I minus, S208 minus 2 reactant decays with first order kinetics. Okay, just like the other reactant. Alright, so now let's fill out what we have calculated already. Okay, so rate is equal to K times S208 minus 2 raised to the what power? A is equal to 1, so that's equal to the first power, times I minus raised to the what power? 1. Alright. I minus. So are we done? Okay, we're not done. What else do we need to calculate? What's left over?
Okay.
How will we calculate K, Bailey? Okay. Pick any experiment, 1, 2, or 3 for me.
Experiment 2.
Okay, so we will use experiment 2 values. You can use 1 or 3. We will use experiment 2 values to calculate rate constant K. But you can use any one. Okay, so what is the rate for experiment 2? Can someone tell me? Okay, looking at my sheet, it's 1.1 times 10 to the minus 4 molar over seconds. Okay. All right, units are going to be a big issue here. What's S208 minus 2 for experiment 2? Okay, 0.080 big M raised to what power? Okay, what power is this raised to? 1, very good. I minus, what's the concentration of I minus for experiment 2? Yes. Okay, raised to what power? Also 1, very good. All right, now we will solve for K. Okay, now we will solve for K. All right, K is equal to, I'm going to move the 0.08 M down. I'm going to move the 0.017 M down. Okay, I'm going to move these two down. Big M over seconds. See that? Okay, M over seconds. 0.080 M. 0.017 M. It's basically solving for K here. All right, units. Okay, because on the exam we have to report the right units. I see students get the wrong units or very, units that are all over the place. So this M cancels out with this M. So what are we left with? M in the denominator, molar in the denominator, and seconds in the denominator. Now we just have to calculate 1.1 times 10 to the minus 4 divided by this product. Everyone see that? So 1.1 times 10 to the minus 4 divided by parentheses 0.08 times 0.017. I'm getting 0.081 M molar in the denominator, seconds in the denominator. Okay? 0.081. Okay? Now, I just want to tell class, everyone to pay attention. I can also write it like this. M to the minus 1, second to the minus 1. Okay, I want to convince you that these two are one and the same. Okay, M in the denominator, I move it up, it becomes n to the minus 1. Seconds in the denominator, I move it up to the numerator, it becomes seconds minus 1. So this or this is either one is correct. So our final answer is this. Okay, so this is what I want you guys to put on any exam or quiz. All right? Let's try to do it right this year, this semester. Okay. Final answer is this. Is equal to K, which is 0.081 inverse molar inverse second. I'll do this way. Times the concentration of S208 minus 2 raised to what power? 1. Times the concentration of I minus raised to what power? 1. Okay, and this is our final answer. Whew, what a problem. Okay, so this is the final answer. I have a way for you guys to know 100% you'll get the right answer on the exam. Okay, how do you know, how can we validate this? How can we check this to see if it's entirely correct? What can we do? It's a rate law. It should work for this equation. Okay, it should work for this equation. And how do we know it's correct? All right, Antoinette, give me a number. But since she said 2, pick a number different than 2. Okay, you'll go with 3. It's okay. All right, so 3. Okay, so we will put values of 3 here. All right, so let's check our answer with experiment 3. Okay. Rate is equal to K. The rate constant for this reaction is 0.081 inverse seconds inverse molar. Okay, what's the concentration of S2O8 minus 2 for experiment 3? You remember? Okay, raised to what power? Raised to what power? Yeah, but what is A? 1. Good. And then I minus. What is I minus for experiment 3? 0.017 m. Raised to what power? 1. Raised to the 1 power. All right, so this m and this m cancels. We will take 0.081 times 0.160 times 0.017, and we get, what do we get? 2.21234 times 10 to the minus 4. Okay, the second stays in the denominator, and the molar goes up, the numerator. And what is the rate for experiment 3? Okay, this is the right answer. This is the right rate law. So we have checked our answer, and it is bang on correct. And even our units are correct. So here we have a way to check our answer to make sure it is correct. Okay. So that is a rate law problem. So we'll have one on the quiz, we'll have one on the exam, and before we take an exam during the review, we'll do one more of these rate law problems. All right, rate expression we also talked about. It will not be on the test, but it's good to have that exposure.